The current process. Although kernel modules don't execute sequentially as applications do, most actions performed by the kernel are done on behalf of a specific process. Kernel code can refer to the current process by accessing the global item current. You see the font change there? Defined in asm current.h, which yields a pointer to struct task struct defined by Linux sched.h. The current pointer refers to the process that is currently executing. During the execution of a system call, such as open or read, the current process is the one that invoked the call. Kernel code can use process-specific information by using current if it needs to do so. An example of this technique is presented in Chapter 6. Actually, current is not truly a global variable. The need to support SMP systems forced the kernel developers to develop a mechanism that finds the current process on the relevant CPU. The mechanism must also be fast, since references to current happen frequently. The struct is an architecture-dependent mechanism that usually hides a pointer to the task struct structure on the kernel stack. The details of the implementation remain hidden to other kernel subsystems, though, and a device driver can just include Linux sched.h and refer to the current process. For example, the following statement prints a process ID and the command name of the current process by accessing certain fields in struct task struct. So we got print k, current info, remember that priority, quote, the process is, so %s, and then PID, %i, and don't forget the new line. The command name stored in current com is the base name of the program file, trimmed to 15 characters if need be, that is being executed by the current process. And then a few other details. Kernel programming differs from user space programming in many ways. We'll point things out as we get to them over the course of the book, but there are a few fundamental issues which, while not warranting a section of their own, are worth a mention. So as you dig into the kernel, the following issues should be kept in mind. Applications are laid out in virtual memory with a very large stack area. The stack, of course, is used to hold the function call history and all automatic variables created by currently active functions. The kernel instead has a very small stack. It can be as small as a single 4096 byte page. Your functions must share that stack with the entire kernel space call chain. Thus, it is never a good idea to declare large automatic variables. If you need larger structures, you should allocate them dynamically at call time. Often, as you look at the kernel API, you'll encounter function names starting with a double underscore. Functions so marked are generally a low-level component of the interface and should be used with caution. Essentially, the double underscore says to the programmer, if you call this function, be sure you know what you're doing. Kernel code cannot do floating point arithmetic. Enabling floating point would require that the kernel save and restore the floating point processor state on each entry to and exit from kernel space, at least on some architectures. Given that, and there really is no need for floating point in kernel code, the extra overhead is not worthwhile.